All right, welcome back. We've got a fascinating topic today, something we're going to really dive deep into. The goal here is to unpack it so thoroughly you walk away feeling like you truly get it.
That's the plan.
Today, we're tackling a classic problem in computer science, especially algorithms. It pops up when you think about making optimal choices under constraints.
Yeah, it's a big one. We're talking about the 0-1 knapsack problem.
Exactly.
And our source material really grounds this in dynamic programming. The knapsack problem is often the go-to example for explaining DP. There are a few flavors, but we're zeroing in on the 0-1 version today. That specific constraint is key.
Okay, let's make it concrete. Imagine you've got a backpack, right? A knapsack. And it has a weight limit. You can only carry so much.
Sure.
And you have a pile of items you could potentially pack. Each item has its own weight and also its own value.
Okay, weight and value for each item. Got it.
Now, the 0-1 part means for any item, you have two choices. Either you take the whole item that's the 1, or you leave it completely behind the 0.
No half measures. You can't cut an item in half or take two of the same thing.
Right. And the challenge is, pack your bag to get the absolute maximum total value possible from the items you choose, but crucially, without going over that weight limit.
It sounds simple enough on the surface. Maybe just grab the most valuable item.
That's the intuitive thought. But, as the source points out, just going for high value or even best value to weight ratio, a greedy approach doesn't actually guarantee the best overall result.
Exactly. Finding that true maximum can get surprisingly complex, particularly as the number of items grows. It's not always obvious.
So that's our mission for this deep dive. We're going to unpack how to solve this thing. We'll look at a few different methods, see why some are, well, better than others.
And really dig into how dynamic programming gives us a powerful, efficient solution, including a pretty neat trick to save on memory.
The aim is to get beyond just knowing the steps, to really understanding the why, so this knowledge genuinely sticks for the long haul.
Let's do it.
Okay, let's unpack this knapsack. So, getting into the core definition from the source material, we have, let's say, N items available.
Right. Distinct items.
For each item, let's call it WGTI1, thinking like programmers with zero-based arrays.
8 of a GTO1.
And we know its value.
Weight and value. Check.
And then there's the knapsack's total capacity, the maximum weight it can hold. We'll call that cap.
Okay.
And the fundamental rule, again, is that 0-1 choice for every single item. Take it or leave it.
And the objective, just to be crystal clear, is to choose a subset of those items.
Right.
Such that the sum of their values is maximized,
Why?
while the sum of their weights stays less than or equal to.
Okay. Now, the source mentioned something about the structure here, because you're making this yes-no decision for each item.
Yeah.
It kind of maps naturally onto a decision tree, doesn't it? Like
Yeah.
you could theoretically explore every single combination of take and leave.
Exactly that. And exploring every single combination is precisely what the first method we should talk about does. Brute force search.
Okay, brute force. How does that actually work for the knapsack? How does it explore that tree?
Well, it typically uses recursion. Think about it like this. For any given item, say item I, and any remaining capacity you have, call it C.
Yeah.
The brute force function recursively looks at two branches. Case 1. You decide not to put item I in the bag.
Right.
The problem then just becomes finding the best you can do with the remaining items, so items 1 to I1, with the same capacity.
Makes sense. What's case 2?
Case 2. You consider putting item I in the bag. Now, you can only do this if its weight, WGTR1, isn't more than the capacity you have left.
Obviously, yeah.
If you can take it, and you choose to explore that path, the value you get is the iter's value, plus whatever the best result is from the remaining items, 1 to I1, using the reduced capacity. See WGTI1.
Okay. So the recursive function calculates both the value if you don't take it and the value if you do take it, if possible. And then it just returns whichever value is higher.
Precisely. The function call needs to track where you are, which item index, and the current capacity C. And it needs base cases. Like if you run out of items or you have no capacity left, the value is 0. You can't add anything more.
Right.
And there's that pruning step too. If the current item is simply too heavy for the remaining capacity, you don't even explore the take it branch. You have to leave it.
Okay. Even with pruning, exploring both branches for every item, that sounds like it could get really big, really fast.
It absolutely does. The source usually shows a diagram or recursive tree, and you can see it branching out wildly.
Yeah.
Since each item essentially doubles the paths you might explore, the number of computations grows exponentially. We're talking time complexity. Where is the number of items?
Oh.
Yeah. That gets incredibly slow very quickly. Even for, say, 30 or 40 items is just astronomical. Brute force becomes totally impractical.
So O's the danger zone. What's the fundamental reason why it's so bad? Is it just the branching?
It's not just the branching, it's what happens down those branches.
Yeah,
If you trace that recursive tree, you start seeing the same exact calculations happening again and again.
How so?
Well, imagine you need to figure out the best value for the first, say, 5 items with a capacity of 10. You might calculate that after deciding not to take item 6.
Okay.
But then, way down a different path where maybe you did take item 7 and its weight reduced the capacity back down to 10, you'd find yourself needing to calculate the exact same thing again. Max value for items 1 to 5 with capacity 10.
Ah, I see. You're repeating the same work in different parts of the calculation.
Exactly. Those are called overlapping subproblems, and they are the key inefficiency in the naive recursive approach.
Overlapping subproblems. Okay, that term rings a bell. And solving that repetition problem, that leads us to memoization, right?
Yeah. Bingo. This is where things get much smarter. Memoization is a technique specifically for speeding up recursion when you have these overlapping subproblems.
How does it work?
It's actually pretty simple conceptually. You just store the result of each subproblem, like the max value for ice the first time you calculate it.
You cache it somewhere.
Yeah, usually in a lookup table or an array, sometimes called a memo. Then, before the function makes a recursive call to solve for icy, it first checks. Have I already solved this and stored the answer?
And if it has?
It just returns the stored value directly. No need to go down that recursive path again.
So you avoid all that redundant computation. That sounds like it would make a huge difference.
Yeah.
How does it change the complexity?
It changes it dramatically. The source explains that with memoization, the time taken isn't related to the total number of recursive calls anymore, but to the number of unique subproblems you actually need to solve.
And how many unique subproblems are there?
Well, each subproblem is defined by the state, the item index from 0 up to n, and the remaining capacity from 0 up to cap.
So about n times cap possibilities?
Exactly. There are n plus 1 times cap plus 1 unique states. Since calculating each state now only happens once, thanks to the memoization, the time complexity drops from that awful down to O times cap.
Okay, that's a massive improvement, moving from exponential to polynomial.
Huge. It makes the problem tractable for much larger inputs.
Right. So memoization speeds up the recursive approach by remembering results. Now, the source also talks about dynamic programming as, like, a third distinct method. How does that fit in? Is it different from memoized recursion?
It's closely related, but the perspective is different. Dynamic programming for this kind of problem is usually thought of as an iterative bottom-up approach. Yeah, instead of starting with the main problem and recursively breaking it down, which is top-down, like memoized recursion, DP starts with the simplest possible subproblems and systematically builds up solutions to larger and larger subproblems until it solves the original one.
Okay, how does that work for the knapsack? What are the steps?
The source typically lays out 3 key steps for the DP approach here. 1, define the state and the DP table. Just like with memoization, the state, DPI, means the maximum value using the first I items with capacity C. But instead of a cache for recursion, we explicitly create a 2D table or array to store all these DPIC values. It'll have dimensions by cap plus 1.
Okay, a table to hold all the intermediate results.
2, identify optimal substructure and the state transition. This is the core logic. How do we calculate the value for DPIC? We think about item I. Again, 2 choices. Either we don't include item. In that case, the max value is just the best we could do with the first I1 items and the same capacity. That value is already computed and stored in our table as DPI1. Or we do include item I, but only if its weight, WT1, is less than or equal to C. If we include it, the value is the item's value plus the best we could do with the first I1 items using the leftover capacity, which is CWGTI1. That value is stored at DPI1, CWGTI1.
So you compare those 2 options, leaving item out versus putting it in.
Exactly. The state transition equation becomes DPIC is the maximum of DPI1C value without item I, and DPI1 CWGTI1 plus value 1, value with item I. If item I is too heavy DPI1C, then you must leave it out, so DPIC simply equals DPI1C. This dependency on previous solutions is the optimal substructure.
Okay. That defines how to calculate any cell based on previous ones. What's the third step?
3. Determine boundary conditions in order. Where do we start? The simplest cases, if you have 0 items or 0 capacity, the max value is 0. So we initialize the entire first row, dp0, 0, and the entire first column of our table to 0.
Those are the base cases, essentially.
Exactly. Then we fill the table iteratively. We typically loop through the items, say from I1 to N, and for each item we loop through the capacities, from fru1 to cap. We fill the table row by row because calculating any cell, DIs only needs values from the row above it, row I1.
So you systematically fill this whole grid using the transition equation at each step. And when you're done, the final answer, the max value for all N items with the full capacity cap, is just sitting there in the bottom right cell, dpn cap.
That's precisely it. You build the solution from the ground up. The source often shows the table being filled step by step. And the time complexity, it's again ON times cap because you're essentially doing a constant amount of work for each of the N plus 1 times cap plus 1 cells in the table.
Same time complexity as memoization. What about space?
Good question. The standard DP approach, using that full 2D table, requires space proportional to the size of the table. So the space complexity is also a core times cap.
Okay, 600 times cap for both time and space. But if people cap get really big, that table could still use a lot of memory, right?
That's the potential drawback. If you have millions of items or a huge capacity, size space might be too much, which leads us naturally to the next optimization.
Do we do better on space? The source mentions space optimization.
Yes, and this is a really neat trick common in DP. Look closely at the state transition. DP I, C only depends on values from row I1. It doesn't depend on row I2 or anything earlier.
Right. Only the immediately preceding row matters for the current row's calculation.
Exactly. This suggests we don't actually need to store the entire table. We really only need the information from the previous step to calculate the current step. The source explains we can optimize the space down to just OCAP using only a single one-dimensional array.
Whoa, wait, just one array? How does that work? If I'm calculating the values for item I and storing them in a single array DP, when I calculate DTC, don't I potentially overwrite the value DPC WGTI1 that I might still need from the previous item's calculation? It feels like I'd be corrupting my own data as I go.
That is exactly the critical issue you have to handle. And you're right, if you just iterate through the capacities in the usual order, from 1 up to cap, you would overwrite the values you need.
So how do you avoid that?
The key insight, as the source points out, is to iterate through the capacities in reverse order. You calculate the values starting from C cap and go down to 1, or technically down to the weight of the current item.
Reverse order, from
Yeah.
down to 1. Why does that fix the problem?
Think about calculating any DPC for the current item. The calculation might need the value of DPC WGTI1 from the previous iteration, item I1. Since CWGTI1 is always less than C, by processing the capacities from high down to low, you ensure that when you compute the new value for DPC, the value currently sitting at index, DPC WGTI1, is still the result from the previous item. You use that older value before your loop gets down to index TWGTI1 and potentially updates it for the current item.
Oh. Because you're going backwards, the values at smaller indices haven't been updated for the current item yet. They still hold the results from the last item.
Precisely. You're using the I1 results before they get overwritten by the I results. The source often has a diagram, like figure 1421 mentioned, that really clarifies how this reverse iteration preserves the necessary I1 state within that single array.
That's really clever. So
Yeah.
this space-optimized DP, it uses just one array of size, cap plus 1, keeps the times cap time, but drops the space complexity all the way down to OCAP.
Exactly right. It's a fantastic optimization when memory is a constraint, and it hinges entirely on that insight about dependencies and the reverse iteration order.
Wow. Okay, that's quite a journey we just took. From brute force, which just explodes,
Right, the nightmare.
to memization. Cleverly solving those overlapping subproblems by remembering results.
Getting us down to O times time.
And the structured bottom-up dynamic programming approach, building that table.
Same complexity, but often conceptually clearer for iteration.
And finally, that slick space optimization, getting the memory down to OCAP with the reverse iteration trick.
It really showcases the power of dynamic programming, doesn't it? This whole process of breaking down a problem, finding that optimal substructure, how the solution depends on smaller solutions, and then systematically building it up. The 0-1 knapsack is just such a perfect example.
And seeing the trade-offs is key too. The raw time cost of brute force, the potential space cost of the full DP table, and then how optimization lets you balance those. It gives you a much richer picture than just knowing one way to solve it.
Definitely. It's about understanding the different tools and when to use them.
So what's the big takeaway here for you, listening?
I think it's that problems that seem incredibly daunting at first, like finding the absolute perfect way to pack that knapsack among countless combinations, can often be tamed. If you can spot those overlapping subproblems and figure out the relationship between the big problem and its smaller parts, techniques like dynamic programming can provide surprisingly efficient solutions.
It makes you wonder what other problems might have that same underlying structure,
Yep.
this systematic way of thinking, find the state, find the transition. It feels like it could apply in a lot of places beyond just weights and values in a backpack.
Which leads to a really important question to ponder. When you're faced with a new problem, especially one that involves making a sequence of choices to get the best outcome, how can you start looking for that optimal substructure we talked about? What are the clues that might tell you, aha, maybe dynamic programming is the way to go here?
That's a great question to chew on. How do you recognize the pattern in the wild? Something to think about as you encounter optimization challenges elsewhere.
Well, thanks for digging deep with us on this one. We hope unpacking the 0-1 knapsack problem this way helps solidify these powerful ideas for you.